All right, so moving on. Now we shall talk about propeller, syncophaser. That's like a synchronizer that uses a phaser.
Just like does it make a cool sound?
It does. If you put your ear close enough to the propeller, you can hear it. All right, so syncophasing sets the props of an aircraft at different or same angles, and that's what we saw in the first picture. It has syncophaser, so you can actually set them. This is kind of cool. What kind of airplane are they depicting here? Skymaster. I know. Look at that, huh? So phase angle of 0, and they are both at the same angle, so you can actually set it to do that, or off by 20 or off by 48, whichever is going to give you a nice, quiet, comfortable, non-pounding ride. So. I don't see that it had it. I do not. Well, that's not anything to do with it. All right. So syncophaser incorporates It incorporates all the features of a synchronizer, but adds propeller phase adjustment. It incorporates the features of a synchronizer, but adds propeller phase adjustment. Phasing is the relative angle between prop blades. So phasing is the relative position of prop blades. All right, so the phaser in the cockpit is going to set the number of degrees of the slave engine past the master. So if I have it 0, 0, if the master is right here, then the slave engine is going to be phased. I'll just do one blade at the same. If I say I want the master here and I want 20 degrees off, then it's going to be 20 degrees off plus 20 degrees minus, depending which way they're going. So they're going this way. So set the, didn't I have a picture there of that? Nope, I didn't. Just a dial shows a little phase angle. All right, so the phaser sets the number of degrees of slave engine past the master engine. And if we go back to here, we can see how far is it past. There's 20 degrees past, 48 degrees past. Well, how does it do it? It uses a pulse generator. Keyed to the same blades. It's like number 1 on the right, number 1 on the left blade. Same blade on each engine. And that, I'll make it nicer. The pulse generator, oops, that's one. The pulse generator will give RPM information as well as position. So all you have to do is key some sensor, like you can have a light sensor. So sometimes you'll see blades that have a little reflective something on it. And so that keys it up. So you can have an optical eye, and every time that blade comes around, the optical eye sees that little piece of tape, and it'll trigger it. So it's going to trigger it, and it'll tell you RPM. Then it also can see the phase. So they're triggering at the same time, then the same phase. It's trigger, trigger, then they're out of phase. And so you can then use that. It'll speed up or slow down the slave engine to get it in or out of phase depending on where you want it. So, if pulses are at the same time, blades are in sync. If pulses are at the same time, blades are in sync. In both RPM and phase. You'll get to experiment a little bit with this, I hope, when you get into one of Larry's classes. You guys are going to do prop balancing, and you do something a little bit similar to this. You have the prop balancer, you put an accelerometer, you bolt it to the engine, and the accelerometer reads in inches per second. And what it does, it measures how fast the engine's going up or down. And then on the propeller, you're going to put a piece of reflective tape, and you're going to bolt an electronic eye, because then that information is going to be sent to a little computer box. And so it wants to know if the engine is swinging up, if it's on an upswing, as this blade comes around, then this blade is the light one. And if it's down, swinging down, when, let's see, the engine follows it, then that would be the heavy one. So, yeah. So then the little box will tell you, you stop it, and it'll say, okay, add so many ounces on the blade where you put the little sticker. So it's kind of the same concept. The control unit will adjust the governor as needed to keep the engine in sync and set prop phase. Control unit will adjust the governor as needed to keep the engine in phase and in sync. And as I mentioned before, a cockpit control, allows pilot to adjust the phase angle.
Ooh.
Scared you. To reduce cabin noise and vibration.
Is the perfect phase recommended anywhere, or do you just have to dial it in and kind of tell it for yourself?
Good question. Juan, what do you know about that? King Airs, they should have this.
I think, no, I mean, I cannot answer the question, but I like to do it a year.
That's what I would think.
And then press the button to hold it.
The phase or the sync?
The same.
So you just sync by ear, because you can really hear it. And that's the thing about it. So I think I started to say about the 310. It doesn't have this, but if the chair works and it can hold the brakes, when we bring up both engines, you will hear them be out of sync. And you can hear it when they get perfectly in sync and then back out again. And it's a little annoying to think about listening to that in and out constantly. On a flight, I would not like that. All right, so that is the synchronizer and the synco phaser. Now let's talk about Autofeathers. Autofeather. So I told you about my time in the simulator with the Citation and knowing that there was going to be an engine fire and perfectly shutting down the wrong engine. And so knowing, it just drove home to me how difficult it would be how easy it would be to do the wrong thing, right? Especially if you're taking off and that suddenly happens during takeoff. And what were we talking about the other day, Juan? We're yawed the wrong way. What was the issue?
Over torque.
Oh yeah, over torque. So yeah, I don't know if you guys were in on this, but Juan was talking about if you're flying along, you have an over torque. So have an over torque on the right engine. Which way is it going to go?
To the left.
That way. Well, if you have let's say we got this 310, 310 is not going to over torque, and I lose an engine, the left engine, which way is it going to go?
To the right.
To the right. So, okay. So I have an over torque on the right engine, it goes this way. I lose the left engine, it goes this way. So I'm flying along and suddenly it pulls back like that. I think I just lost my left engine, right? But the right one's over torquing, but I think my left one's going bad. So what do I do with the left one? Shut it down and feather it. Well, that's the wrong thing to do because the problem's on the right side. So, it's you have to troubleshoot things like that. And of course, you have an engine that quits. Who's been out with me and the Skymaster where the front engines quit? And it's kind of unnerving, isn't it? We're sitting on the ground with absolutely nothing to lose. I mean, worst case scenario, you guys have to push it back. I don't even, it's like, and it's still unnerving to watch the prop stop when it shouldn't have. And you're looking at the gauges and you're like, what happened? And, now imagine that on a takeoff roll. So there's a lot going on. And I tell you that to say that wouldn't it be nice if there was something that could detect this and take care of the problem for you? And of course, that's an Autofeather. So if you put it on Autofeather, then what happens is it can sense when the engine has lost thrust. So it'll be like a thrust sensor or something. And I've worked on airplanes where a thrust sensor was nothing more than like a very small pitot tube, which is just an air sensor tube that was mounted in the bottom cowling somewhere behind the propeller. So the bottom cowling. So it actually, it sensed the thrust from the prop. If you lost the prop, of course, it's going to get some air from forward moving of the aircraft, but there's a significant difference between the air behind the propeller and the air from just slipstream. So the engine quits, you'll get a loss of thrust. And some of them even, this plane I'm thinking of didn't have Autofeather. It simply had an indicator light to tell the pilot which engine just lost thrust. So it's just something as simple as a little pitot tube going through a pressure transducer that picked it up and would do that. But anyway, so you can actually get something with an Autofeather where when it loses the thrust, it can actually just automatically feather the engine. So it's something that the pilot doesn't have to think about. Well, I'm here to be thinking about it, trust me, but think about two things. One, shoot, I just ruined a perfectly good pair of underwear. Two, the engine just... typically used for takeoff and landing only. I don't know why. You don't use it all of the time, I guess. I don't know. Do you know?
Yeah, it's just for some people claim that it could trigger a feathering situation with weather. Because the one I know is linked to the throttle. So there is a circuit that you need to press the thing on, and the throttle needs to be at max power.
Okay.
So if there is some surging or something in the engine going on because of weather, you don't want that propeller to feather.
Well, I don't want that to happen on takeoff either.
Yeah, but,
I know, just joking. It's the lesser of two evils. All right. So the system that I've got notes about, when armed. Wow, I just didn't even spell that word right. When armed, system is activated with power levers above 50%. When armed, system is activated with power levers above about 50%. Causes prop to feather if torque pressure switch senses a drop below preset limit. Now, didn't you guys in Phil's class look at some torque pressure sensors in some of the engines? The Garrett one, I think. All right. Causes the prop to feather if torque pressure switch senses a drop below a preset limit. The time delay will prevent the feather if there's just a momentary power loss. A little burp or fart in the engine, it will not do it. Time delay will prevent a feather if there is just a momentary loss of power. One or 2 seconds. Do you know how long 1 or 2 seconds is in an aircraft that just had a loss of power?
1, 2.
Yeah, it's the exact same amount of time it is when the rest of the world. Do you know how long it feels like? All right, here's the good news. If one prop is feathered, if one system will not auto feather a second engine. Why do you suppose that is? Yeah. It's like, look, I already lost one engine. Why don't you just deal with what you got over here? I think I'd rather. Huh?
What do you have an uneven drag?
Yeah, then feather it yourself.
Oh. Oh, that doesn't stop you.
Right, doesn't stop you from doing it. It just doesn't do it on its own. You have to put your beer down and do it yourself. And if you have, then you got to reach back and get a new one.
That's why that chair does that.
And why do I keep calling it a chair? It's a seat. I keep doing it. Every time I say it, I'm like, oh, is this the wrong thing? Yes, we don't have a chair. The sofa. I shall refer to it as the sofa. Gosh. The seat. The seat broke. Chair.
No.
I knew I needed to lose a little bit of weight, but come on. All right, I got to move this. I'm just looking at Justin over here.
I'm good.
He's happy. All right. All right, so we talked about those 3 prop systems, right?
Kevin, you know, on the 4 blade,
Yeah?
if the auto feather doesn't work, it's a no-go. They're grounded.
Oh, really? That's not on the MEO. I wonder why on the 4 blade, but
Because it's just
too much drag on the 4 blades.
It's just too hard to.
So, yeah. All right. Well, we can move right along then. Something a little bit different. Propeller ice. That's the name of a boy band, and
How would you?
I have daughters. All right, so you're going to get a lot more stuff about ice when you get into ice and rain control in second year, but I want to cover props prop icing because it is kind of the prop section, so we're going to discuss that. So propeller ice or any kind of ice accumulation is a pretty serious event on an aircraft. Number one, it starts adding significant weight to the airplane. Number two, it destroys the airfoil shape. So you destroy the airfoil and you add a bunch of weight, the airplane doesn't fly so well. So we'll talk about some ice stuff later. Well, I guess it's in my notes. We'll get to that. So we will write that. Just kind of go as we go. Accumulation of ice causes loss of the airfoil shape and prop imbalance. I should have mentioned that one, yeah. So if it's on a wing, it's just going to ruin the airfoil and get heavy. You put it on the prop, and if it doesn't accumulate exactly even, then you get out of balance. Or worse, it starts accumulating and you get rid of it in an imbalance. It's like you have 3 blades or even 2 blades and one prop loses its ice and the other blade doesn't. And then you got an imbalance situation. So that gets to be a problem. So accumulation. Yeah, that's right. Good point. It'll just shake the other ice off. What are you worried about? Just run it up. Accumulation of ice causes loss of airfoil. Airfoil shape and prop imbalance. I don't think the weight on the prop is such a big deal.
Is it more prone to forming on the front or back of the plane?
I think leading edge.
Leading edge.
I think. I've never been in an icing situation to shut off the prop to take a look. All right.
What do you think
They're not the surface of them isn't big enough. As opposed to the wing, the surface of the wing is huge. So you can accumulate a lot of ice on the wings and create a lot of weight. I think the amount of ice that would accumulate on a propeller just isn't enough to be a weight issue. It's more of a loss of an airfoil and imbalance issue than it is a weight issue at that point. Just like the rest of the airplane, they wouldn't say it's an imbalance issue, even though you can get more ice on one wing than the other. It's like, well, that's not the big thing here. On that, it's weight and loss of airfoil. So icing, not the good kind that goes on a cake, does not usually occur near the outboard or outer sections of the prop. Tends to only collect near the hub and out so far.
Makes sense.
Well, why does that make sense?
Because it's spinning much faster on the outside, so it's much harder for the ice to actually stick on it and build up.
You're partially right.
Versus
It sticks to the paint, but that paint slid off. Since the paint's just sliding off anyway, just taking the ice with it.
Totally just screwed him up again.
What, I screwed him up again?
Yeah, totally just screwed him up again.
This poor guy. One of these days I'm going to get a call from a DME going, what are you telling me? No. What? The temperature?
It's a speed.
Well, I don't think so.
There isn't that.
No, so fast.
Yeah, maybe it is, but from a mechanics standpoint, it doesn't matter to me. I don't think so. I think he's right, that it's just the centrifugal forces are just, so maybe there is a temperature difference, but when we're talking about you're talking about what? Not talking about 5 or 10 degrees, we'd be talking about fractions of degrees, I think. I'm just making up stuff. I don't know here. The point is, when we look at de-icing systems or anti-icing systems for props, the first thing you're going to notice is, hey, how come they're only in the first 18 or so inches near the root? What happened to the outboard? How come you're not putting them out there? Well, the answer is ice doesn't accumulate out there. Why? Well,
Slides off.
slides off the paint. All right, near the outboard sections of the prop. I have due to centrifugal forces.
It actually forms, but immediately gets thrown out.
Yeah, it slides off. Well, of course, because it's going to form because it's there. It's cold. And it's hitting it. It just goes away. So really, all we really needed to do was spin the inboards faster, right? All right, let's talk about two types of, I don't like how I wrote this, but I'm writing icing systems. Of course, they're not systems to make ice, they're systems to get rid of ice, so I should...
De-icing?
No, I don't want to write de-icing. There's a specific reason, two types of no ice systems.
That's the same as.
Get rid of ice systems. No, that's even wrong. No ice is what I want to go with. No ice systems. No ice systems. Yes, that's the improper word, and I'm going to use it that way for a reason. One, because, this should be an I, because there's such thing as an anti-ice system, and this prevents accumulation of ice. So in other words, it didn't let it get there to begin with. So if we were looking at a wing, we'll do this first. There's anti-ice and de-ice. I'm going to spell it that way just because there's anti-ice that way. And that is removes ice once built up. So if we were to look at a wing and what kind of ice systems no ice systems we have there, we could say, well, this particular wing, they have an anti-ice system. Well, how does that anti-ice system work? Well, it takes bleed air and it runs it across the leading edge, and it keeps the leading edge so warm that ice can never form. It just melts as soon as it hits it, and it's just water. All right? Or we could have a system that injects a chemical through the leading edge that changes the temperature of the freezing of water, and it doesn't let water freeze. All right, so that's anti-ice. Or we could have a de-ice system, which says, well, you got to let it build up and then get rid of it. And one of the ways that that is done is that we have the leading edge of the wing, and must have a different color. And on the front, there's a little boot with sections on it, and it just looks like a rubber boot. And what happens is the ice, which shall be blue, accumulates, and this red thing here is a bladder. And what it does is it has sections, and it's there. That section, every other one is going to expand, and it's going to break off the ice and make it go away. And so that would be one way to do de-ice. Of course, when you look at a system like this, you got to be really careful, because if you were a little panicky and you decided to turn it on kind of prematurely, what happens is all these little bladders are expanding and contracting, and so what you do is you actually end up building the ice up over top of it. So the ice would just come out and kind of build a little cavity, and then inside of here, the little bladders would be filling up and not breaking it off. And so they just build a little igloo in there for themselves, and then the ice just gets thicker and thicker and thicker and thicker.
So how do the bladders fill up?
With air. So they use two things. They use pressure air, then vacuum air, then pressure air, then vacuum air. It's got vacuum on it all the time to keep these bladders from being pulled out from the slipstream and up. Say it might be sucked down to the wing. So, all right, so that's a wing. Now, wing is real easy to plumb pneumatics to. Try doing that to a propeller that's spinning around.
Really long hose.
It's got a really long hose, and then every now and then you got to stop the engine and back it up to unwind the hose, right? So that wouldn't work. So for our we're talking about our ice systems here. So for anti-ice, to keep ice from forming, we can use chemicals or heat. Now, of course, the drawback to chemicals are you've got to have a storage tank. It's got it's got a limited capacity. Or you can use heat, which is the more common way nowadays, and it just has heated boots. And so it has rubber boots with heating elements in there, and they're going to heat up. And I'll show you how those work. And then you can go de-ice. I'm just trying to think. I can't think of a really good de-ice system, but
I always thought the King Air had a boot system on the props.
they do have boots, but they don't inflate.
No, they're heated.
And that's kind of why I brought that up. But it's very funny because even as a mechanic examiner, you'd be surprised how many people would tell me, oh, they're boots. Well, how'd that work? Oh, it's simple. They inflate. Really? How's that work? So, all right.
Any pictures?
Any pictures? I've got some of my vacation if you want.
Is this the one where Zeus ate him in the hand?
This is one we're going to talk about, the fluid ice system. Fluid ice system. And this is part of the fluid ice system, which we'll talk about. But note the boot on here, how it's glued down there. See there, well, I know this is a fluid ice system because I can see the nozzle. But it's got a boot on it. So what's a boot for? Is it got both heat and this? No.
Guide the fluid.
It guides the fluid down these little veins is the word I was looking for. Thanks. And then we're going to talk about the de-ice system or anti-ice with heat. So we'll talk about that. And that is the same boot. It's very differently. That's the boot for electric system. All right. So there's your pictures. Get off me. All right, where am I? Blackback. Ooh, blue. Hey, like blue. Anti-ice. All right, so we have anti-ice fluid, which we'll use isopropyl alcohol, also called IPA.
That's a good beer.
Is it? So if somebody offers you some IPA, I don't know. All right. What's the downside?
Corrosion.
Wait.
I was thinking flammability. But obviously, I like that. There's weight added to it. Corrosion? I don't think this.
Same as TKS.
Oh no,
Okay.
no, it's rubbing alcohol. You have to have the weight. You have to have the system. Limited supply. Or we can use phosphate compounds. I think that's your TKS. Downside is cost.
Isn't that also flammable?
Never tried.
Phosphate?
The book that I got this out of, that's exactly what they said, and that's what I'm going with. It's a special non-flammable. That's what the phosphate makes it.
The road complains with corrosion.
Corrosion. Let's see. Anti-ice must be used before the accumulation of ice or the formation of ice. Because anti-ice, oops, that was just went wrong. Anti-ice does not melt ice. So if it doesn't melt it, you got to get it on before the ice forms. But then that becomes a problem, as I would think. It's when do you turn it on? You know, now you have that problem. Do you turn it on, and if you turn it on too soon and you run out of fluid, then what do you get? Well, now you can't fly anymore. Now you got to land to get some more fluid. So there's this whole problem with doing this, right? So
Probably the ice buildup would be first noticeable on parts which are not moving.
Uh-huh.
As soon as you see an ice building up,
Okay, now you got ice building up.
So then turn it on.
He's going to build up on the prop first, I think. The prop's going to be colder. It's moving more. Got that pressure drop around it. So I think, okay, by the time it starts building on the wings, it's already built on the prop. Then it's too late. See the problem? This is the problem I would have with this system. It's like, ooh, I want to turn it on, but I better not because, then I'm going to run out. But if I wait too long, then I can't melt it off.
I would still think on the wing roots it would build up first there and then the prop.
Couldn't they design the system to be able to upgrade almost as long as the endurance of the aircraft?
No.
Flight now.
No?
All right, operation. A tank.
Spraying more alcohol constantly when you go along.
What do we need? A tank that stores the fluid is plumbed to a slinger ring at the prop. A tank that stores fluid is plumbed to a slinger ring at the prop. Okay, well, let's go to picture. All right, so we got our tank through a filter. We got our switch. What's a rheostat?
Resistance.
Oh, a dial.
Dimmer switch.
Dimmer switch. I like dimmer switch.
I know what we thought.
So what's the purpose of having a rheostat going to an electric pump here?
You can control it.
There you go. Control what?
The amount.
The amount. Yeah. Is it really icing bad, or am I just I'm a little concerned about it? I'm a little concerned about it. I don't know. Turn it on real slow. Ice is building up on the wings as fast as we can keep up with it. Well, I'm going to turn it all the way up, right? So all the way up. So we got the pump. Pump's going to feed it out. We got two engines, right and left engine feed pipe. So because this here, the prop is spinning and this is not, you can't have it connected or it will get wound up. So what happens is this is just aimed inside. See, there's a little cup right here like that. So this is going to spray it inside of there, and that fluid, thanks to centrifugal force, will force the fluid into this cup, where it will come in and be forced into this nozzle and run down the prop, causing the de-ice on both sides. Pretty simple, isn't it?
How does the, oh, I see, so the hose distributes the alcohol onto the slinger ring,
Yep,
and then goes from the slinger ring through the nozzles?
yep.
It's not like on a bearing system where it just
Nope.
squeezes out or anything?
Nope.
Okay.
This slinger ring is nothing more than just the back of the prop. It's got a piece of aluminum that looks like that. And if I drop bigger, the hose just comes like that. And so the fluid comes through here and just collects. Of course, this is the dish, goes all the way around. You have to think 3D. And so it just goes in that little dish. And at two spots, there's two little holes that correspond to this pipe and come out, or however many holes we have for props. Follows the little feed nozzle down there, just runs down onto the rubber that has guide vanes and just keeps it evenly going down the prop.
We have one of these on one of the props.
We do. I think two of them maybe. So yes, we do have these out there.
Let's do that.
All right, so fluid is pumped to slinger ring at the prop. The slinger ring collects the fluid and through centrifugal force sprays the fluid onto the base of the blades. The slinger ring collects the fluid and through centrifugal force sprays the fluid onto the base of the blades.
Wouldn't the slinger ring have to have vanes to help it?
Doesn't.
Is there a seal?
Nope. It's wide open.
Just uses like centrifugal force just to
Yep.
throw it out to the sides.
Yep.
And the pressure too.
Well, there's enough pressure in the pump to spray it into the little
Into the whole 13 hole.
into the slinger ring, and that's it. Just once it's in the slinger ring, it's the centrifugal force keeps it from going anywhere else.
It's like swinging a bucket over your head.
But that has to make it contain it.
Huh?
But that has to make it contain it.
Bucket over your head?
If you swing a bucket of water,
Yeah.
the bucket's containing it.
Yeah.
Yeah,
The
it's
ring is contained.
and so is this. It's because of this the C shape of it. We'll do that because of this. Because of the shape. And remember, it's 3D all the way around. So if that's looking at it one way. If I look at it the other way, it's it's a circle.
I mean, I just assumed it would have veins in it. Like,
Doesn't. Nope. And just put one little hole coming out like that, and there you go. So it'll slosh around and find its way to right there. A pilot control, which was the rheostat. Will vary the amount of fluid released to meet conditions. Will vary the amount of fluid released to meet conditions. Lots of ice, lots of fluid. Not so much ice, not so much fluid. A check valve that opens at 3 to 5 psi is also in the system, but yet not shown on here. What do you suppose a check valve that opens at 3 to 5 psi would be needed for?
Right by the slinger ring.
Maybe right here?
Yeah, that's what I was thinking.
Possibly that. Makes sense to me. Why would I need that?
So that you wouldn't get air in the line all the way back, so you had some pressure right there.
Well, what kind of pressure systems do we have around here? High or low pressure? Suppose you got low pressure there. Lower than this pressure. It's going to suck it right through the pump and out. So I don't want that. So you got a check valve. So the check valve is going to keep that closed. And so even though you've got a pressure differential between the two of maybe a pound or two, that's okay. It's not until the pump turns on that's got at least 3 psi that's going to open up these check valves that it's going to bypass. So
So maybe that you have a steady
Ball on the
spray
spring.
out.
it just keeps it from leaking out. It's not a steady spray. It doesn't matter because once you get in the slinger ring is going to do its thing. So you just don't want it being sucked out of the tank when you don't want it.
None of that, you don't want it to unprime the pump too.
I suppose that's oh, there's another picture. I don't know. Does that help? Probably not. Same thing. And there's you can't really see the slinger ring too well. That's the best picture of it. And there's the discharge nozzle with the boot. Check valve that opens at 3 to 5 psi prevents fluid from being sucked out of the tank. Some aircraft, and by some I mean all the ones I'm familiar with, use feed shoes. Feed shoes are rubber boots with grooves or channels that direct fluid down the blade. And feed shoes, feed shoes only cover about 1/3 of the blade. All right, that brings me to de-icing. So that was my anti-ice, one system, de-icing. Technically speaking, de-icing allows ice to form and then removes it. Do you have de-ice boots on your plane?
Yeah.
All right. Thought you mentioned that. All right, this particular one uses heated boots. So, accomplished. With the use of heated boots. Bonded, which means glued, to the prop.
Hey Kevin, when we have lunch on Wednesday, we're gonna clean and then come to test early. That's what you're worried about right now? I was thinking, you know.
Well, so I'm glad you finally started. I was wondering if any day now that's going to kick in.
I'm not waiting till last day of school.
So, tell you what,
Gotta be thinking about tonight, bud.
we'll turn this off here.